Mr. Dean here for yet another video. This time, complex numbers. Let's get right to it. New numbers. Three basic ways of solving a quadratics, and that'll lead us to our complex numbers. Number one is factoring. All right, factoring is great. It's usually pretty fast for a quadratic. It's usually pretty simple, but there's definitely times where it's very difficult, if not impossible, and factoring does not get you anywhere. This example in the middle, you cannot factor it using integers, so we're in trouble there. Number two, completing the square. All right, another way of solving quadratics. Although it gets a bit dicey if the leading coefficient is not 1. So let's say there was a 3 here. It gets definitely strange. And even if there's not a 3, there's just a 1 there. If there's an odd number for b, it gets pretty complicated because you're going to be taking half of that and squaring it. You end up with fractions and decimals and whatnot. So the third way always works. It's the quadratic formula. The only problem is that it's a little more complicated and takes some time, but it does always work. So if we're really bent on trying to solve this quadratic and find out what numbers solve this, we're going to find out, if you use that quadratic formula correctly, that the discriminant is a negative number. Now, what happened in the history, just as recently as 600 to 700 years ago, if they had a negative number in the square root, they just throw out the answer, throw out the problem, and just say, the heck with it, we don't know. There is no answer. And while it is true there's no answer in the real number sense, there's no x-intercepts here, you don't see anything. The vertex are way up here in quadrant 1. What if they kept going and decided to invent a new number? Well, that didn't occur until about 500 years ago. So it's time for this new type of number to join the club. You started off with natural numbers, all right? And not only is this the history of the order that numbers were discovered or invented, it's also the history of how you learn numbers in school. You started with natural numbers. You worked your way up to whole numbers. Your first conceptual number was 0. There are whole ancient societies that never had a 0, like Rome never had a 0. Then we worked your way towards negative numbers. Again, more conceptual. How can you possibly have a number that's less than 0? How can you have less than 0 of anything? So it was more of a concept, and it got the word negative associated with those. And negative kind of has a bad connotation, of course. So people weren't sure exactly how to use them or what they would do. A negative times a negative is a positive. That's very difficult to explain. And so, but that time, though, once you accepted these, you had all the integers. All right? Next came fractions. I'm not sure what grade you start to learn fraction, but it's pretty early. You start with basic fractions. But then you realize that there's numbers in between all the integers. All right? There's an infinite number of rationals between every integer. All right? And they can be expressed as a ratio, so we call them rational numbers. And that was pretty good for a while. Then, the ancient Pythagoras had to have known and just kind of ignored irrational numbers, because Pythagoras, if you give him a square sides 1 and you tell him to use Pythagorean theorem to find the diagonal, it's going to have to be square root of 2. And there's no decimal equivalent to square root of 2. There's no fraction equivalent to square root of 2. The decimal goes on and on forever. It does not repeat in a pattern. It just goes on forever. It made them crazy back then to think that they existed. And so, just like with negative square roots, the Pythagoreans and other societies would just throw out that idea that there actually could be a number like that, and they were considered crazy. So irrational, of course, means crazy and not making any sense. But at that point, it took a couple hundred years, and then they were accepted, and you had now all your real numbers. Now, real numbers weren't called real numbers until the discovery of imaginary numbers. Once again, another bad name. It almost sounds like they're useless, that they don't exist. But that's exactly what they thought about irrational numbers, and it's exactly what they thought about negative numbers. So the history of it is that they discover a number that they think will never be used, and then a certain time frame later, they realize that they're used quite a bit. It was hundreds of years that imaginary numbers were used in math, And it wasn't until really the last 30 to 40 years that we've realized how useful they are. All right? So now we have all numbers that we'll be using in pre-calc can be considered complex numbers. So let's talk about this. So, the very first mention of people trying to use imaginary numbers dates all the way back to the 1st century. Heron of Alexandria, yep, the same Heron of Heron's formula for the triangle. He's credited with inventing probably the first steam engine, believe it or not, way back then, like a couple thousand years before the Industrial Revolution. He's pretty amazing. He was studying the volume of an impossible section of a pyramid, and that's where he kind of stumbled upon these square roots of negative numbers. So once negative numbers really got invented, mathematicians tried to find a number that, when squared, could equal a -1. They didn't find an answer, so they just threw it out. And for a long time, no one really studied anything to do with that. But behold the Renaissance. Yes, the Renaissance. That picture in the background is a classic picture from the Renaissance. In the mid-1500s, Girolamo Cardano wrote a book titled Ars Magna, and he solved an equation that if you just multiplied this through would look more like a regular quadratic, and he found the answer to be 5 plus or minus the square root of -15. And instead of just throwing out the answer, he worked with square roots of negative numbers, although he did say that his work would be as subtle as it would be useless, and referred to working with these numbers as mental torture. Can you believe it? Let's try some mental torture right now. We'll add and subtract complex numbers. We have a definition now of square root of -1. Instead of throwing it out, we're just going to say that that is equal to this number I. All right, it's not a variable, it's a number. And if instead of throwing things out, let's just see what we would do if we were to just add numbers together. All right, so if you have a number 2 minus 8i, we're going to add that to another part of it. We just add like terms. It's not too painful. I would get an answer of 5 plus 3i. I saw 5 minus 3i. All right. Now, complex numbers are always written like that. They're written with a real part and a complex part. The real part is written first, and the imaginary part, so I should have said imaginary part, is written second. That's the imaginary part with an I. And all together they make a complex number. All right? What's kind of interesting is we've been dealing with complex numbers all our lives, just that the imaginary part was 0. So if you take an innocent number like 12, that's a complex number actually. It's just that its imaginary part is 0. So we usually don't even bother saying that part. Let's move on to an example over here again. Just want to try some basic math and see if our regular rules apply. Yeah, you can just subtract that away. 12 minus 3 is 9. And the negative distributes over, and I have 9 minus 5i. So far so good. We'll call this our final answer. We cannot get 4i out of this or anything like that because they're not like terms. So the rules for like terms for adding and subtracting are much the same as they always have been. Now it gets a little weird with multiplying complex numbers. Let's take a look over here at our kind of helpful diagram. So we have I is the square root of -1. All right. I squared, that's not a very good I. I squared equals -1. I to the third power would be -1 times another I. So it'd be -I. I to the fourth power brings you all the way back to 1. And you keep on going with this. I to the fifth power, all the way around, and I to the fifth is equal to just plain I to the first power. All right, so this diagram kind of describes that relationship. So on the left-hand side, let's start doing some problems. Now what you don't want to do with this is multiply -9 times -25 and get a positive number. Because that concept or that rule with multiplication can't really work with the negatives there. What we really have to do, the square root of -9, we have to think of it as the square root of 9 and break off that negative part like that. All right? we're going to do the same thing with the 25. We're going to take the positive 25, we're going to break off that negative part. So I have 3i times 5i. The square root of negative 1 is I. And that becomes 15i squared. Now I squared is negative 1. Got that right there. So we have our final answer is negative 15. Let's try another example here. This one, we need to distribute everything to everybody. Just got to do it carefully here. So I have 2 times 9 is 18. 2 times 4i is 8i. We have a negative 9i. And finally, we have a negative 4i squared. All right? Bring together your like terms. And remember again, I squared is negative 1. So we're going to multiply. Negative 4 times negative 1. And this here, this whole part, will be positive 4. All right? That makes the 4 and the 18 like terms. So I'm going to bring it together. I'm always going to write my real part first, which is 22, and then my imaginary part second. All right, final answer 22 minus I. All right, last one here. Let's do this one in blue, I guess. Let's go 4 times 16i, or plus 16i, I meant to say. We have a minus 16i, and finally we have a negative 64i squared. Again, I squared. I squared goes back from the imaginary world to the real world. We have negative 1. So this is really positive 64 over here. Notice these middle terms for this particular problem are going to cancel out. And this 4 is just going to come down. The final answer is 68. So you can get a real answer, a real number answer, out of something that started imaginary. Dividing by complex numbers. Dividing by complex, this is where things get a little complex. We're going to use the complex conjugate, all right? Complex conjugate is fancy word for change the sign in the middle and multiply top and bottom line by that. It's a lot like rationalizing the denominator, if you remember that. This whole thing is equal to 1, so we're multiplying by 1, all right? So we change the sign in between the denominator, all right? We don't worry about the numerator right now, we just change the sign of the denominator in between. And we're going to multiply it all through, and you're going to see what's going to happen. We're going to get an answer that is complex. So multiply everybody times everybody. So that would be, if I do the math right at the bottom, 9 plus 6i minus 6i. See that? That's going to get rid of those i's. Our last term is going to be negative 4i squared. And that's our denominator. These middle terms are going to cancel. And I have 9 plus 4, right, on my denominator because I squared changes the sign. I squared is negative 1. So my denominator is 13. On the numerator, I'm just going to be careful of multiplying everything through. 6 plus 4i, 12i, and finally 8i squared. 8i squared is really the same as minus 8. These they won't of course cancel, but they'll combine, and I have 6 minus 8. So I have negative 2, and I have 12i. Positive, no, 16i. 16i. The only part I would change to this answer is that I want it to be in that a plus bi form. I want to separate the real part from the imaginary part. That's just standard protocol. So we're going to go negative 2/13. We're going to add that to 16/13 I. So that's 16/13 I. That would be my final answer in complex form. All right. Complex numbers. They get exciting. They get cool. This is iteration of the Mandelbrot set. There was a man named Benoit Mandelbrot, a mathematician who just died a few years ago. He's got some YouTube videos. He's got a TED Talk that's really interesting. And the last like 20 years, really in the last 5, people have really gone nuts with the graphing of Mandelbrot sets. The Fractals is already a band name. I never heard this album, but it's out there. Of course, there's lots of math jokes. Now you can understand them a little bit better. See, this is one of my favorites. All right. Now, I want to show you one of those videos I'm talking about. Let's go online. All right. Bear with. So there's lots of videos online. This is a YouTube video. You can just type fractal or fractal zoom or anything like this. Obviously all made with computers, but this is all based on imaginary numbers. It's kind of loosely based on simply a graph of complex numbers. And I mean, this particular video goes on for 3 hours long. I will spare you, and we will see you in class. Everybody take care. Thanks for watching.